Yes. Over to you, Ram.
Okay, so can everybody see my screen? I
Yes.
assume yes.
Yeah.
Yeah, thank you. So today, as you all already know, we'll be studying about inversion. So it's just a topic in geometry. Essentially, inversion is just a transformation. So what did so like, it's like a transformation? Like you have other transformations like say translation. You have translations. You have rotations. You have say reflection. So these are all some simple transformations. However, inversion is slightly different from these in the sense that all of these like preserve the shape of the figure, whereas inversion does not do that. So I'll first define what an inversion is. So in inversion, you take a circle with center C and radius R, and you do the following. For any point, for all points A, A maps to A dash such that A dash lies on CA, the ray CA, and OA times OA dash is equal to R square. So I'll explain what this actually does. So say we have a circle. Uh, this is center C, and say we take a point A on this. So A will map to a point A dash here such that you have CA times CA dash equals R square. Okay, so is everybody clear with the definition? Any doubts? A thumbs up.
So that means that like
That's
A dash
definition.
will also be mapped to A.
Right. That is going to be that is going to be my next point. Correct. So A and A dash actually swap places. So as Lavish said, right?
Please tell the bad things. I was not in the class.
Okay, okay. So essentially what I said is that we are talking about inversion, which is a geometric transformation. So in inversion, you have like a circle with center C and radius R. And then for any point A, what you do, you map it to a point A dash such that A dash lies on the ray CA and OA times, this should be CA. CA times CA dash is equal to R square. So this is how the inversion transformation is defined. And now we are just discussing that if a point A is mapped to A dash, then A dash is also mapped to A. Is this clear? Because if you take point A dash, say A dash maps to B, then you have CA dash times CB equal to R square. But you already know that CA times CA dash is R square. So that just means that CA equals CB, which implies A equals B. So essentially, if 2 points swap places in an inversion.
Going to be directed.
Sorry, lengths are not directed. So as we mentioned in the definition, A dash lies on the ray CA. So what happens is that A dash will also lie on the ray CA and not on the other side. If you wanted to keep it on the other side, then you can do a reflection, and that is what we call that a negative inversion because you reflect it. Or you can also think of it as multiplying like the instead of R square, you can think of having CA times CA dash to be equal to minus of R square in some sense. We're talking about directed lengths. But we will just think of it as doing a reflection about C. Okay, so now can someone tell me where will so if I have a circle with center C and a point A inside the circle, where will A go? Will it be outside the circle, inside the circle, or on the circle?
Outside.
Correct.
Outside.
Because if you have CA times CA dash equal to R square and CA is less than R, then CA dash would be greater than R. and vice versa. If the point is outside the circle, it will be in the circle, and any point on the circle will stay the same. Great. So another question is, okay, suppose I have a circle and circle as center C. I have 2 points which are inverses, A and A dash. Question is, how do I construct A dash geometrically from A? Okay. So does anybody have any ideas as how we can do this?
If we have length CA and diameter and the radius, then we can compute.
Yes, you can compute that, but then how will you do it using, say, ruler and compass effectively? Okay, I see someone has written tangents from A dash, correct. So what actually happens, you can do is this, you can construct tangents from A dash or like draw this perpendicular line A. So suppose I have circle, center C, and I have a point inside, I'll call it A. What I'll do is I'll draw this ray CA. I will draw this line perpendicular like this, and I'll construct the tangents. Okay, and this point becomes A dash. So why does this work? Is because since this is tangent, I'll let this point be P. Then you have CPA is 90 and you have CAP also to be 90. So what you get is that triangle CAP is similar to triangle CPA dash, which implies CA times CA dash is equal to CP square. Often this definition is also useful to like spot inverses in a configuration or in a geometry problem. So this is a nice way to look at inverse points. Okay. So now let's look at what happens to a line under an inversion. Before that, we'll see what happens to 2 points. Suppose if you have points A and B, and A maps to A dash and B maps to B dash, then what can you say about these 4 points? Does anybody know?
A prime, B prime, B is cyclic.
Correct. Can you also state why?
Power of point.
Power of
Correct.
point.
Right. So by definition, you have CA times CA dash equals to CB times CB dash. But then this is just power of point, right?
Yes.
So this just forms a circle. And now this gives us a nice property about points and their inverses in terms of angles. So if you have 2 points A and B, you get angle CAB is equal to angle C B dash A dash. So this is a nice property, which you can often use while angle chasing. So if you take a diagram and you invert it about a circle, then you can you can use this angle relation to angle chase later. Okay. So let's see what happens to lines under an inversion. So suppose I have this point C and okay, Bhairav, I think you have a doubt.
Yes, what happens to the center of the circle? Because if you take the perpendicular line, any diameter, then the two lines are parallel.
Right. So center of the inverse of a center of a circle is not actually well defined. So what we say that we say sometimes it is at the point of infinity, or sometimes people just leave it like that. So if you end up studying projective geometry, there's a notion of point at infinity. Like instead of having saying two parallel lines do not meet, we say that two parallel lines meet at infinity. So that all kind of goes into projective geometry, which we won't go. So we'll just assume that the center goes to point of infinity or it does not have an inverse at all. You can use either of the two inversions. I mean definition, sorry. Okay. So when you are taking a line, there are two cases, right? The line either passes through C or it doesn't. So if a line passes through C, then this is pretty straightforward what happens to it, right? because every point on the line will still stay on the line. So this line L through C is preserved. Okay, so this was not that interesting, but let's look what happens to a line not passing through C.
Sorry, I don't get what is preserved here.
So preserved as in like if you have lines, this line L, after you perform an inversion, this line won't change at all. The points on it will swap with each other on the line itself, but the line as a whole does not change.
So the point will not go outside the line.
Right. So any point on the line will stay on the line, and any point not on the line will be not on the line after inversion. So the line just stays the same after inversion. For example, if you look at translation, so in translation, nothing is preserved, right? Because you moved everything from a non-zero distance like this, you shift it. If you look at a rotation, so if I have a point center O and A, so if I rotate this with some angle, say 30 degrees, counterclockwise, then A becomes A dash, right? So all points except O is rotates with some angle, whereas O is the only thing which is preserved. Do you get it?
Yeah.
Cool. Okay. So let's see what happens to a line L not passing through C. So what we do now is we take the foot of perpendicular from C to this line. I'll call this, say, X. And well, let's look at any point not other than X on line L, say A. So what do you see here? You see that CX is 90 degrees, right? However, if I'm looking at the inverses of A and X, then what I'll get is that angle CXA would be equal to angle CX dash A dash, which is 90 degrees. So if I look at the inverses, X should come, okay, X will go out, will go inside the circle, but to not clutter the diagram, I'll keep it outside. So if A will become something like this, and X will say come here. So you have angle CX, you know CX is 90. So this is, so you'll have angle C A dash X dash to be 90. Right. Does everybody understand why this happens, why this is true?
Yeah, the cyclic quite little thing.
Right. So because of this result. So now what does this mean? So if you look at the image of X and call it X dash, then for all points A on this line, this relation will be true, right? But what does that mean? That means that this will actually form a circle with diameter Cx dash. So what does this imply? This implies that all lines not passing through C become circles passing through C. Does everybody get this? Any doubts?
Yeah, got it.
Cool. So now what is so this also means that every circle passing through C would become a line not passing through C. As like inverse, like if you invert 2 times, you get the same diagram back. So you get that any circle passing through C also becomes a line not passing through C. So now let's look at the last case of a circle. If you have a circle C, your center of inversion C, and if I have a circle like this, can anybody guess what happens to it? This is a question. This question is for people who have not seen inversion before.
I think it translates to a line.
Okay. Other people?
Radical axis.
Radical axis, okay. Anybody else?
Same figure inside.
Same figure inside. Okay, there are some nice guesses. However, what
They're taking
happens
the
is that,
inverse of the circle.
yeah,
That's the
inverse of
question.
this circle. So you have a center C,
Oh, sorry, that will be a circle.
right? Okay, so somebody got it. What happens is that the circle still remains a circle. Let's look at the proof also. So now suppose this circle is say O1, and I'll draw this line. This becomes the diameter, and this will be points say A and B. So now again, A would map to say A dash somewhere here, and B will map to B dash. And you get this circle now. So let's look at what happens to any point X on this line, on this circle. So this should intersect this somewhere like here. This will be X dash. So let's look at what happens to angle A dash, X dash, B dash. So angle A dash, X dash, B dash would just, so now the only like relation with angles we know of with respect to inversion is this lemma we proved here, right? So we'll try to fit this in. So I can rewrite A dash, X dash, B dash as angle C, X dash, A dash minus angle C, X dash, B dash. Now from our lemma, we know that this is just equal to Cx dash A dash would be Cax minus angle Cbx. So Cax minus Cbx. However, this is just the exterior angle theorem, right? So this is just going to be angle AXB, which is 90.
And yeah.
So you get that A dash X dash B dash is equal to angle AXB, which is 90. Essentially, all points on the circle will also become a circle. Okay. So does this imply that the centers that O1 will map to O2?
Thus, there will be a change in ratio.
Sorry?
Thus, there will be change in the ratio of radius.
Okay. So yeah, there will be a change in the ratio of the radius. And in fact, you can also try to calculate it afterwards. I'll also be giving like, we'll also be discussing what happens to lengths in an
Okay,
inversion. So what do you think? What will happen to will the centers swap with each other?
Yep. They have to swap each other.
Why should they swap though?
Because we learned now that if actually we have not proved it yet that it is inversion.
Okay. My claim is that the centers do not swap with each other.
Wait, how can they even swap? Like it shouldn't swap actually.
Okay, why do you think so? Do you have a proof?
No, I don't know.
Okay,
It
no
just
problem.
seems irrational that it'll swap.
Okay, so we'll try to prove this. So suppose this circle becomes this circle afterwards, then these should have a common tangent, right? Okay, these circles are not that great. Yeah. So if I have these two circles, so if this line will map to this line on the circle, and since the circles are inverses with respect to each other, there can be only one such point. So essentially, this line which is tangent to one circle will be tangent to the other circle. Now let's look at what happens to the centers here. So if this is the center, I know that this angle is 90. So what does that mean? Where will this point map to? Can anybody tell? If this is P and this is P dash, and this is the line, where will P dash map to? Where will O1 dash map to?
P dash
A line
90
parallel to OP.
Line parallel to
OP.
OP. Okay. So then that means,
because it will form a cyclic quadrilateral, na? So
right,
the center will make the p dash as 90 degree. So it must be in perpendicular parallel.
but if it is parallel to OP dash, then that means that these two lines, so that means it forms a trapezium, right? It does not form a cyclic
Yes,
quadrilateral.
it
And the
will also form
trapezium,
a cyclic quad.
trapeziums can be cyclic only when they're isosceles. So that means this trapezium has to be isosceles.
Okay.
It will be like P dash say perpendicular on the line CO1.
Right. This will be perpendicular. Do you see why? This is because again by the lemma, you have CPO1 equal to angle CO1 dash P dash. So I'm just using the lemma here. You just swap these 2 points. So, and we know that CPO1 is actually 90 degrees, which means CO1 dash P dash is going to be 90 degrees. And we know that O1 dash will actually lie on CO1. So essentially it's just the foot of the perpendicular. Okay, cool.
Also, we can't say that P dash or O dash will be perpendicular because it has to be a rectangular, which is not possible.
Right. Okay, cool. So here's a small exercise. I'll give you all to try. Prove that these circles are homothetic. This should be kind of obvious by now, but just for the sake of completion, I'll let you guys try to prove afterwards that the two circles are indeed homothetic. Okay, someone said done by similar triangles. Right, you can probably do that. Yeah. Okay, so now you have seen what happens to lines, what happens to circles, what happens to angles under an inversion. Let's see what happens to lengths. So if I have, say, center C, and this is going to be A, B, and then A dash, A will map to A dash, B will map to B dash. So how can we predict A dash, B dash? Does anybody have any idea?
Angles,
Sorry?
angles and similarity.
Right, similar triangles. So you have triangle CAB similar to triangle CB dash A dash, which means that you have CA by CB dash equal to AB by AB dash. Sorry, this should be A dash B dash. Right. Does everyone get this? Why does this happen?
Yeah,
Good. So we now have A dash B dash equal to AB times CB dash by CA. Okay. So let's see what we can do with this expression. This will become, say, AB. I'll multiply the numerator and denominator by both CB. So this will become CB dash by CB, CB dash times CB by CA by CB, CA times CB. So now by definition, we know that CB dash times CB is just R square, right? So essentially this just becomes AB times R square by CA times CB. Does everyone understand this?
yeah, got it.
Okay. Has everybody else understood? Because I'm hearing only one person.
Yes.
Okay,
Yes.
nice. Cool. So let's do a problem. Someone in the beginning told me that about Ptolemy, that's what I was going to discuss also. So we'll prove Ptolemy's inequality. It states that if you have a quadrilateral in general, A, B, C, D, then you have AB times CD plus BC times AD is greater than or equal to AC times BD. Okay. So okay. So does anybody have any ideas as to how to approach this? One big hint is that this is an inversion lecture, so inversion is somehow involved.
We could first try by drawing the circle around the quadrilateral if it's cyclic, since we're talking about Ptolemy.
Yes, but we don't know that it's cyclic. It's not necessarily cyclic. It's a general quadrilateral.
So like any three of them, suppose ABC, their
Okay.
circle, and then wherever D lies.
So somehow this is a very bad circle, but let's work with this. Okay. Then okay. So the idea I was going for is because see, if you invert with this circle, you get that A, B, C are preserved, obviously. However, you do not have any nice information about D, right? Because if this is the center O, then you don't have any nice information about OD, or you will have to use it. Could be possible, but then it will be slightly cumbersome.
Can I join AB and DC?
Okay, AB and DC, then
Uh, then the intersection point will be the inversion point, inversion center.
okay, you invert with say well, let's call this E. But then again, you but you can't use power of point here, right? Because you don't know anything about these 3 points. You can say you can invert with radius E root of EA times EB, that will swap A and B, and then D will go to some point and C will go to some point. We, we don't have nice control, and you don't even have information about like, then again you kind of get the same inequality, right?
Okay.
So max to max, what you can have is like AB improved. Okay, so I'll give a hint. Okay, somebody has written inversion about circle centered at D. That's actually that's actually the proof I was going for. You can invert at any point with respect to any power, it does not matter. Since someone has suggested D, will go with D. So you D will be here, then A dash will go somewhere, B dash will go somewhere, C dash will go somewhere, C will go to C dash. And now what happens here is that uh, A dash, B dash will be equal to, by the formula we shown above, it will be equal to AB times R square by dA times dB. And you have B dash C dash equal to BC
So we
times R
can do
square.
this for all of them and then apply the triangle inequality.
Right. Correct. Is times dB times dC. However, the thing here is that we won't be using this version. If you would have seen the calculations above, I could have also gone ahead this way. Instead of doing this, like here we use CA by CB dash equal to AB by A dash B dash. So I'll instead solve for AB here. You have AB equal to A dash B dash times CA by CB dash. So I'll multiply CA dash in the top and bottom. So then this will give us AB A dash B dash times R square by CB dash times CA dash. This also works because then this is again the inversion formula applied to A dash B dash. Because AB maps to A dash B dash and A dash B dash maps to AB. Does everyone understand why this is true? Or is there anyone who does not understand this?
I understand it, but like, how is this useful?
Right, we'll see. So you know that now AB is equal to A dash B dash times R square by dA dash times dB dash. Similarly, you have equations for BC, CA. And what happens to dA? dA will just be R square by dA dash. This is by definition of inversion. So let's look at the inequality. So the inequality states that AB times CD plus BC times AD is greater than or equal to AC times BD. So this is true if and only if AB becomes A dash B dash times R square by dA dash times dB dash. CD becomes R square by DC dash. BC will become B dash C dash times R square by dB dash times DC dash times, and AD will become R square by dA dash, and this will be greater than or equal to A dash C dash times R square by dA dash times DC dash times R square by dB dash. Now, if you look at it, all the denominators have dA dash and dB dash and DC dash. So all of this gets cancelled, and R square also gets cancelled. So this just reduces to a nice inequality. A dash B dash plus B dash C dash greater than or equal to A dash C dash. However, this is just the triangle inequality, as I believe Ronit had mentioned before. I hope I'm pronouncing your name correctly.
I have one doubt in this.
Okay.
Why are the lens like AD, CD, and BD written like that? I couldn't really get that.
ADCD. Okay. So D is the center of inversion, right?
Oh, okay, got it. By
Yes. So DA
definition.
dash, so that's just by definition. Whereas the earlier formula we had proved, we had assumed that A and B do not lie on D, or they are different from D. That's how you get that not so good formula, whereas for this is slightly better. Okay. So now what happens at the equality case? The equality case only occurs when A dash, B dash, C dash are collinear. But then what does this imply? This implies that A, B,
Because
C, D are concyclic. So this also proves Ptolemy's theorem, which you might have seen, which is the more popular version. Okay. So does anybody have any doubts till now?
Yeah, like what was the motivation of taking D as the inversion point?
So I think maybe one case is like I don't really know the motivation as such, but when I'd seen the problem, it was mainly like looking at the equality case where it forms a circle, right?
Motivation can be that like D, we do not know about D, so we can take center as D.
Right. That's also another motivation, because if you're trying to somehow use inversion on this problem, then working with any other point does not give you that much information. Whereas if you have D, then you already have one point in your control, and others are just, you can use the distance formula. However, what I feel is somewhat the natural idea is that if you look at the equality case, when you have a circle, so if you inverted one of the points, those 3 points just form a line. Whereas in other cases, it will form a triangle. So essentially, there could be some play of triangle inequality in the proof.
Okay.
Great. Okay, I would prefer if you all don't annotate on the diagram on the screen. Thank you. Okay, so let's prove another statement. This is actually another well-known lemma. If you are inverting, say, if you have two circles, C1 and, okay, I'll not name them C1, I'll name them omega. So if you have two circles, omega 1 and omega 2, then, and say you invert at or with respect to omega 1, then omega 2 is preserved if and only if omega 1 and omega 2 are orthogonal. I'll explain what this orthogonal means. So you can just think of it as follows. If my circles are, say, omega 1 and omega 2 with centers C1 and C2, and let the intersection points be A and B, then essentially C1A is tangent to omega 2 and C2A is tangent to omega 1. Or you could think of it as like the angles the angles between the circles is 90 degrees. It's not a really precise definition, but the angle between curves are defined using the tangents. So you can think of it as like the angle between the tangents is 90 degrees. Has everybody understood what this means? Orthogonal circles?
Yeah, got.
Cool. So let's see what happens when we invert with respect to C1 or with respect to omega 1. So I have C1. Let's say I have AB and then this should be tangent. This will be somewhat like this. These are equal, but these look equal, but orthogonal circles need not be equal as such. Omega 1 and omega 2. Okay. So let's look at any point. This say I'll call this point B, and let's look at what happens to B dash. So obviously B dash must lie on C1B, right?
So
We said
sec
B maps to B dash. So I know B dash lies on C1B. That's by definition. And I also know that C1B times C1B dash is equal to the radius square. But what is the radius? The radius is just C1A, right? C1A square. However, C1A is also the power of C with respect to omega 2. What does this imply? This
it is
implies that B
some.
dash lies on omega 2. Sorry?
Yeah.
Right. So essentially this is very nice, right? Because now you have B and B dash swapping, which means that any point on the circle swaps to a point on the circle itself. And in fact, these come in pairs. So you have B and B dash swapping. So if you take any line through C1, these 2 points will swap with each other. So that's a really nice thing. Because sometimes you want to take an inversion and you want to really work with the circle, then you can just preserve it and then you just have point swapping instead of them going to random places. Okay. So now we have looked at what an inversion is. Let's just kind of summarize what all we have seen till now. So inversion, one is a definition. So you either invert, so you invert with respect to a circle C with radius R, such that now here all points A map to A dash, such that one, A dash lies on the ray CA, and two, CA times CA dash is equal to R square. This is the definition. Then if A maps to A dash maps to A. Again, then if you have any 2 points A and B, then CAB is equal to CB dash A dash. Then we look at what happens to circles and lines. So line through C is preserved. Lines not through C swap with circles through C. And circles not through C becomes some other circle not through C. It need not be the same. And we also had a look at the distance formula in some sense for inversion, which is A dash B dash equals to AB times R square by CA dash with CA. Yeah, CA times CB. And then eighth, given omega 1 and omega 2, omega 2 is preserved under an inversion with respect to omega 1 if and only if omega 1 and omega 2 are orthogonal. Right.
Actually, in fifth point, the C actually talks about the circle or the center. I'm getting a bit confused
Center.
here.
So I've defined here. So you have a circle, center C and radius R.
Can you please show the fifth point again
It's on the screen. Are you not able to see it?
in the slide when we did it?
Okay.
And speaking of which, could you also like show 6 point also? I forgot that as well.
Okay, so okay. If you can just take a screenshot of this, I would suggest pretty quick. If you want to note it down, then we can note it after the class, so then the flow does not get disturbed. So I believe this should be the
Okay,
sixth point,
done.
and this is the fifth point. Yeah. You can just take a screenshot pretty quick if you want to.
Done.
Okay, cool. So this is essentially what all we have studied under inversion so far. And you can quote all of this on Inmo, so don't be afraid. Now what we'll do is that we'll have a look at some common inversions that we see. These inversions like frequently appear in Olympiads. Common inversions. So the first is orthocenter related inversions. So mainly there are two inversions here. So if you have say a triangle ABC, and then I drop the perpendiculars D, E, F, and H is orthocenter. So there are two like common inversions that you can do with this. One is an inversion at H. So inversion at H with radius minus root of minus HA times HD. Now this feels a bit weird, but essentially what we are doing, you can think of this as inverting with HA, root HA by times HD, and then a reflection at H. So what does this do? So what is HA? So like, you know that since these are 90 degrees, all these angles are 90 degrees here. You know that AEDB is cyclic. You have that AFDC is cyclic. You have BFEC is also cyclic. So you have three cyclic quadrilaterals. And then if you use power of point on H, you'll get that HA times HD is equal to HB times HE, which is equal to HC times HF. So what happens? So if I look at say point D, D will become somewhere, will come here, A dash, so that HA dash is equal to HA. Now if I reflect with respect to H, D just goes to A. So this inversion just swaps A and D, B and E, and C and F. So what does this do? So this essentially maps ABC to 9-point circle, right? So again, this
Um,
is right. Sorry.
I like we are mapping from A to D with respect to which circle?
So you invert at with h with radius root h times root hd, and then you reflect at h. Is it clear?
Okay.
Good. So ABC maps to the 9-point circle, and then now again the further properties depend on what problem you're solving. Sometimes this is useful to prove certain lemmas. Sometimes it's used to do the whole problem also. There is in fact one IMO problem. Do not recall the year number. I'll put it in. Maybe we can put it in the preset also. I'll find it and put it. Put one problem on this type of inversion. Then another second type of inversion is at A, which is also related to orthocenters. A, B, C. And then this is D, H, E, F. Okay. So now I invert at A with radius root AH times AD. Okay. So where do you all think the other points will map?
A will go to D.
A will not go to D this time because we're inverting at A.
Oh.
And we're
H
inverting at A
will
with
go to
this
D.
radius. So where would D
H will
go?
go to D.
Right. H will go to D. Correct. So you have H goes to D. What happens to B and C?
They will go to E and F.
Sorry?
They will go to F and E, sorry.
Right. Why is that?
Because it is cyclic BFHD and
Correct.
HB.
So as these two angles are 90 degrees, this will be a cyclic quadrilateral, which means AF times AB is equal to AH times AD. So so root AH times AD is the same as root AF times AB. So that means B will swap with E, and B will swap with F, and C will swap with E. Again, there are some properties you can exploit here. I'll not talk about them right now because I will be talking about different other inversions also. However, I've not seen this inversion quite frequently in math Olympiads. So yeah. Okay. So let's look
Actually, I
at,
have a doubt in the first.
right? Okay.
What if HA is equals to HD?
HA is equal. Uh, so what will happen? Like, then that just means that H is like, so then it will still map to each other, right?
But won't it be the case when either both the points are in the circle or both the points outside the circle like that?
No, that doesn't matter because now we are reflecting at H again. Then the whole thing kind of changes, right? Even if a point inside the circle will be outside and then will again map to the same point. So here, if you look at the proof, what we did, this we are nowhere using the fact that A or D is inside or outside the circle. It's completely just dependent on cyclic quadrilaterals, which is always true.
Okay, got it.
Okay. So let's look at incircle inversion. As the name suggests, you invert with respect to the incircle. So if I have, okay, triangle ABC with incenter I, then D, E, F as the touch points. Okay. So if I invert with respect to DF, where do you think A, B, C will land up? I'll give you, okay, I'll wait for 1 minute and then I'll give you a hint.
Would they land on the sides of triangle DF?
Okay, correct. Why?
We can draw these lines, AI, BI. So they are, so each of them,
Would it be perpendicular bisector of FE?
Right. I mean, AI is the perpendicular bisector because you have these two triangles
since
congruent.
IE is going, since A is going to be the tangent, AF, since they're all tangents, it's just the thing we use to invert 2 points. Since
Right.
A is the tangent,
Right. So this will end up on this. Yeah, this will end up being AI intersection FE. Or you can also think of it in this way. You have AFI to be cyclic, right? Because both are 90 degrees. So since AFI is cyclic, then AFI is essentially a circle passing through the center of inversion. So that will become a line not passing. So that will become a line not passing through I. But you already know that F and E are preserved because they lie on the circle. So essentially you get that AFE maps to line FE, which means that A, and since A lies on I, A dash lies on I, this I dash will just be equal to EF intersection I. And as someone pointed out before, this is just the perpendicular bisector, which implies that A dash is actually the midpoint of FE. So B dash will map to midpoint of FE and C dash will also map to the midpoint of FE. Cool. So let's look at, okay, let's do a problem on incircle inversion. Suppose I have triangle ABC with in touch triangle DEF. Let the circumcenter be O, center of circle be I, and let H be the orthocenter. H is orthocenter of triangle DEF. So can you prove that I, O, H are collinear? Prove that I, H, O are collinear. I'll give you 2-3 minutes to think about it. Know that we are using incircle inversion here. That's already one hit. So I'll just lay out the sketch. Sketch as in the inverted figure, what all we have. So A will map to A dash, B will map to B dash here, and C will map to C dash here. Okay. And these are the midpoints. So what can you say? Okay, so what can you say about the circumcircle of A dash, B dash, C dash? Is that a nice circle? Think of it with respect to DEF maybe.
A dash, B dash, C dash will be the 9-point circle of DEF.
Correct. Good job. So this is the 9-point circle. Point circle. Right.
So,
And okay. So
yes.
let's draw a slightly cleaner diagram now.
So then it will be on the same line as I and Hatch, but then because because the centers are homothetic, it has to be on the same line as I and O. So then
Right.
Hatch and O have to be on the same line.
Correct. Good job. So I'll just draw a slightly nicer diagram. So as Bhairav said, if this is O, this is I, let's call the 9-point center N, and you have H. So it is well known that I, N, H are collinear. Collinear. Why? Because I is the circumcenter, N is the 9-point center, and H is the orthocenter.
Which is the
Euler
homothet.
line. Yeah. So this is the Euler line of triangle DEF. However, as Bhairav mentioned, since N is the circumcenter of A dash B dash C dash and O is the circumcenter of A, B, C, you have INO collinear. You also have INH collinear, which implies H lies on IO, and we are done. Has everyone understood the proof?
With NIO, how collinear? NIO.
Because O is the center of circle ABC and N is the circumcenter of circle A dash B dash C dash. So as we saw before, if you have these two circles, even though the centers do not map to each other, they are collinear with C.
Oh yeah. Yep.
Right. So
So here the I. C is I here.
right. So you get INO collinear, which implies IOH collinear, and you're done. So let's look at one more inversion before we go to a contest problem. This is a very interesting inversion. We call it the root BC inversion. And this is one of my favorites because in this, lots of points, map to lots of nice points. And then, okay, I'll just show it to you. So what we do, you have again, obviously, triangle ABC. Okay, no, I can't draw a line now. Yeah, this is better. So I have ABC. And what I do is I invert at A with radius root of AB times AC. This is the first step. And second step, I reflect about the angle bisector. Does everyone understand what we are doing?
Can you please tell what is this reflect point? I couldn't get it earlier as well. Like what does this
Okay.
mean?
So essentially, if I have a point O, and okay, I'm talking about point A. So when I reflect A about O, essentially I just take like, so you can think of it as a 180-degree rotation when I'm talking with respect to a point.
Yeah.
So you're reflecting with respect to a point, I just rotate it 180 degrees, and then A becomes A dash. But if I'm reflecting about this time, I'm reflecting about a line. Right. So if I have a line L and this is A, this is just become A dash. So essentially, if you have done those SOF IMO problems, you have like find the water reflection, mirror reflection as such. No.
Which angle bisector is being talked about here?
Angle bisector of BAC.
And what are the points essentially like? Which points will get reflected?
Right. So that's what we'll be talking about now. No, so all points get reflected. It's just so you're doing this on the whole plane. Inversion is not on any specific, you can't just invert on specific part of the diagram and leave the whole part diagram like that. You can use the original diagram in your inverted figure, but you can't just say, okay, I invert only on this section and I leave the whole section like that. So whenever we are doing a transformation, essentially we are looking at the whole plane, whole Euclidean plane, to be more precise.
Okay.
Okay. So what happens to B? So B will first go to a point, say B star, such that now you have AB times AB star equals root of AB times AC whole square. Right. This is by definition what we are doing. This is just AB times AC, and then AB gets cancelled. AB star is just equal to AC. And then when it's reflected about the angle bisector, B star just goes to C. So essentially, B and C swap with each other. Do you all understand this?
Yeah, now got it.
This is kind of forced, a forced inversion. Now let's see what happens to other points in this. Okay, one note. Say I look at 2 points. If I have any point A, B, C, and say P becomes P dash, then you have AP and AP dash to be isogonal. Does everyone know what isogonal means, or has it not been covered yet?
Yes.
Okay,
Yeah.
Yeah. Reflection about angle
angle
bisector.
bisector, right? Or in more simple terms, PAB is equal to P dash AC, or PAC is equal to P dash AB. So this is what you get for P and P dash in terms of AP and AP dash. So now let's look at what happens to other points under an inversion. Suppose I look at say the circumcenter. Okay. Can you guess where the circumcenter goes?
Orthocenter.
Not really, but it will lie on the line AH, but
Okay.
it need not be AH exactly. So you can use the fact that, okay, I have AOB to be 90, AOB to be 2C degrees. So then when it switches, I'll get so AOB is equal to 2C. Okay, I'll not use 2, I'll use 2 times angle ACB, otherwise it will get confusing. So AOB is equal to twice of angle ABC. So then that means AOB would be equal to angle A, B dash, O dash. But B dash is just C, right? As you saw before. So you get that angle ACO is equal to twice of angle ACB. So essentially, this is going to be something like this. O dash.
AC, right? ACO
Sorry?
dash.
Yeah, ACO dash is twice of angle C, which is angle ACB. Is your doubt cleared? Or were you trying to say something?
Got it.
Okay. Now the same thing will happen for B also, right? These two angles will also be equal. So essentially, O just becomes the reflection of A in BC. Does everyone get this?
Why is AO dash not collinear?
Sorry, though it's not collinear because we are also reflecting about the angle bisector, right?
Okay, okay. Got it.
So you get AHO collinear instant. So this just implies that A angle S lies because this is perpendicular, right? This is O dash is the reflection of A. So you get these 3 points are collinear. Now, what do you think will happen to
Wait,
the
does
instant?
that mean that A, B, C, and O dash are cyclic altogether?
No, this will not be cyclic, right? If this was cyclic, then you would have that BOC is the pre like
Oh,
if you
yeah,
have
yeah, yeah.
yeah
Yeah,
B O
that
dash
makes
C
sense.
dash and A cyclic,
Hmm.
then if in the previous image in the pre-image in some sense, B was C, C was B, and O dash was O. So then this would be collinear, which is not the case.
Right.
So you can always use this normal like things to check if your claims are true also. Because if by mistake suppose you think this is a very simple example, but sometimes in more complicated diagrams you might get confused. So like if this were to be cyclic, then these 3 points are collinear. So in this case, this is not true. So that did not happen in my diagram, in my inverted diagram. So let's now look at what happens to the incenter I. Now obviously I dash will lie on AI, right? Agreed?
Yeah.
Okay. And I know angle AIB is equal to 90 plus C by 2, right?
Yes.
So that implies angle AB dash I dash would also be 90 plus C by 2, but B dash is just C. This is angle ACI dash is equal to 90 plus C by 2. Right, so this were to be I dash, then I would have this is 90 plus C by 2, which implies angle BCI dash would be 90 plus C by 2 minus C, which is 90 minus C by 2. If you look at this, if I extend this angle is also 90 minus C by 2, right?
Yeah. It was like BIC circumcircle.
Sorry?
BIC circle of BIC. That point.
Right. Yeah. Okay, so essentially you have CI dash is the external angle bisector, right? In other words,
Yeah.
so if CI dash is the external angle bisector, I'll get BI dash also to be the external angle bisector, which implies I dash is actually IA, the excenter. So you also have IA swaps with IA. Is this clear?
Yeah. Clear.
Okay. Now again, there are lots more properties with this. If you have studied some config geo, then you would also know that uh, the Humpty and Dumpty points also map to some special points. I don't know if there's been a config geo class yet. If there may be, then I guess you will learn over there about these points, or you can also learn on your own about Humpty and Dumpty points. So now we conclude with contest problem. Let me just get the image. Okay. I see someone has put 2015 P3. Okay. Oh, that's the ortho center problem, right? So we'll just post this. Let's see. Right. Okay. Can you all see the question?
Yeah.
Okay. So let's do this. This is a slightly hard problem. It is Elmo 2010 P6. So Elmo is just a problem which they hold in their version of IMOTC called the MOP, which I guess the juniors conduct for the seniors. Also, seniors conduct for the juniors over there. Like in India, we have Lama. In US, they have Elmo. Elmo is the original version, though. Okay, so let's draw the diagram. Question is slightly bigger. Okay, so I'll just draw. What is this happening? Okay, I'll just draw a normal line. Okay, so I have a circle ABC and circumcircle is omega. In center is I. You have also the AX center, IA, and you have the arc midpoint M. Let's see what all is defined. So then D and F are the in-touch points, the in-touch and X-touch points. So be somewhat like this. E. And then you have a circle tangent to BC and tangent to the circumcircle. Contact point is T. Then you have TI intersecting the circumcircle again at S. And I want to show that SIA and ME intersect on the circumcircle. Good. Has everyone understood the problem?
Can you show the problem statement as well?
Yeah. Okay, I'll just zoom in a bit on the statement. Okay. So should we continue? Has everyone taken note of the statement or the diagram?
Just a sec.
Good. So let's make some initial observations. If you have studied homotheity, then you know that MDT is collinear. Why? Because if you take a homotheity at T, then which sends this circle, this, okay, I'll call this circle, have they given a name? No, okay. I'll call this say gamma. So it sends gamma to omega, which means that it will send D to M, since it will send the center of the circle to O, and then you have OM parallel to ID and all of that. Then that just means that D goes to point M. I hope everyone knows this lemma. If they don't, then I can explain it again. Does anybody have any doubt?
I don't know actually.
Sorry?
I don't know that lemma. Can you tell again?
Okay. So let's look at a circle. I have a chord and I have a circle tangent to this. Now, if the circle is tangent to this as, okay, I'll just use the same, this thing, T, I, D, and O. So if I take a homothety at T, which sends this small circle to the big circle, then it should map T, then, okay, diagrams, again, not that good. So so I should map I to O, right? You agree?
Yeah, tangent, because it's tangent.
Right. And then D should also map to certain point, call it M. Then you have OM parallel to ID because it's a homothety.
Yeah.
And if OM, and you know that ID is perpendicular to BC by definition. So that means OM will also be perpendicular to DC, which implies so since like that means OM is actually the perpendicular bisector of BC, which implies M is the arc midpoint.
Okay, got it, got it.
Has everyone else also understood this?
I is the center, right?
Yeah, I is the center of the I isn't, yeah, I mean, I can be, I is not, in this case, I is the center. In here, I is not the center.
Yeah,
But the center will lie on line ID only because it's perpendicular. Okay. Also, another fact here is that MD times MT is equal to MB square. Why? Because if M is the arc midpoint and say T is any point here, then since these both are equal, these two angles will be equal. So which means that MT actually bisects angle BTC, which means that angle MTC will be equal to angle MBC. And if I call this point D, then you have triangle MDB similar to triangle MBT. You all agree with this? Because these two angles are equal and this angle is common.
Why are the two angles equal? That
Because
BT
M is the arc midpoint. So that means that MTB will be equal to MTC and MTC is equal to MDB because it's circle.
Oh
Just
yeah,
like
yeah. Okay, got it.
cool. So then if you just use spiral similar, sorry, just similarity, then you get that MD by MB is equal to MB by MT. So this implies MD times MT is equal to MB square. And T is not necessarily the specific point. It can just be any line passing through this, intersecting at D and T. So this actually motivates the inversion that we are going to do here. So if you look at ME, let it intersect this point at X, then you also have here that ME times MX equals to MD times MT, which is equal to MV square. And it is well known that M is the center of the circle BICIA, right? Because this angle IBIA is 90 and M is the midpoint of IIA. So you have ME times MX equals MD times MT equal to MV square, which is MI square, which is also MIA square. So now you have, so point being that all of these points satisfy lots of nice properties. So what we do is that we invert with M and radius MB. Before that, what we'll do is that so now handling S is slightly weird, right? Because we don't know much information about the line TI as such. So what we'll do is that we'll define X as ME time ME cap circumcircle. And then instead of showing that ME and IIS intersect on the circle, we'll show that TI and XIA intersect on the circle instead. Okay?
Hey, can you write some statements as well? Because it's hard to follow when you speak up.
Sure. So we'll redefine X is equal to ME cap circumcircle omega or ABC only. And now we want to prove that TI and XIA intersect on ABC. This is equivalent to the original statement. We just redefined X and now we're trying to prove it for T. Has everyone understood what all we are doing and why we are doing this? Okay, I assume yes.
Yeah, yeah.
Right. So now let's have a look at what happens to the inverted figure. I have a circumcircle and this is triangle ABC. This is in center I. So note that B, I, C, and IA will actually remain constant because the circle we are inverting is basically BIC. So since we are inverting with respect to BIC, A will swap with this point. I'll call this point A dash. And D will swap with T. So essentially this is D dash and this is T dash. Then this point is E. So E essentially becomes X dash and this point is E dash. Great. So originally what we wanted to prove was that Ti and IAE intersect on ABC. So let's look what this becomes. ABC will become line BC, right? Because B and C are fixed and ABC passes through M. So ABC now becomes line BC. Can anyone help me understand what IAE becomes?
It becomes IA E dash.
No, because IAE is a line not passing through M, right?
So it'll become a circle.
Right. So it will become a circle passing through. So sorry, this should be IA X, my bad. So IA X will become a circle passing through M. Since IA remains the same and X becomes X dash, so it will become circle M IA M X dash. So you want to show that this circle, and if you look at TI, T becomes T dash and I remains the same. So you want to show that these two circles actually intersect on BC. Right? Has everyone understood this?
Yeah.
Cool. Okay. So let's say this circle IA M X dash intersects BC at S, or okay, S is already used. So intersects BC at K. So I know that angle K X dash, sorry, K X dash IA is equal to 90 degrees, which implies angle K MIA is equal to 90 degrees, which implies angle K M A is equal to 90 degrees. Okay. So I have this angle to be 90 degrees. Now what I wish to show is that now if you look at this, I want to show that K lies on M T dash I, right? Does anyone see the finish now?
Yes.
Cool, can you finish it?
Yes, so then it's just IMK is equal to 90 degrees and ITK is equal to 90 degrees, so they're concyclic.
Great. So this is essentially done, right? I'll just write this down. So let M IA X dash intersection BC be X dash comma K. Then angle KMIA, which is 90. So 90 is equal to angle KMIA, sorry, angle K X dash IA, which is equal to angle KMIA, which is equal to angle KMI, and which is equal to angle. So KMI is equal to 90 degrees, and this is also angle KTI.
KT dash I.
Yeah, sorry, KT dash I. Thank you. So this implies that I T dash M K is cyclic. Has everyone understood this?
Yes.
And since they are cyclic, this implies that their pre-images actually concur at the circumcycle. Now, a few remarks here, if you note that K is essentially S, right? Because if these two circles map at K, then the pre-image should map to S. So essentially, K is the inverse of S with respect to BIC inversion. Do you understand this?
Yeah.
Right. And note that we show that KMA is equal to 90 degrees actually, which actually implies that A is the reflection of A in the diameter. S is the reflection of A in the diameter, which is a pretty cool fact as such in general. Also, if you have studied some config geo, T is the Sharkey Devil point. Sharkey Devil point, or We also call it the spy point. Spy point is slightly uncommon, but it's usually named as Sharky devil. Sometimes people also call it spy point. So T is the spy point, or the Sharky devil. So those of you have heard about this can it's a good fact to know. Those of you who haven't, you can learn about this through Google or somewhere. Okay, someone is asking, where would I get config geo resources? Uh, there is one PDF called Murica. Yeah, I'll put the name in chat. 2, 3, 4, 5, 6. So you can just search this up on the net. You can put Murica AOPS or something, and then you'll get it. This is a PDF containing lots of config geos materials. So you can just go through those and study those if you want. Some of those use inversion and projective geometry, but then you can just skip those parts. Okay. So from whatever I had planned, we are done with the lecture. Does anybody have any doubts? If not, then we can do some another simple problem on inversion. Does anybody have any doubts, or do they want to copy something? You can let me know. Okay. I assume not. Has everybody understood the solution to this problem though? This is a pretty nice problem how inversion like just kills the problem, because at beginning this seems like a very hard problem, whereas if you just invert it, it's just a like simple one-line angle chase. Okay, so let's do another simple problem. Say you have okay, there are messages. Okay, so Nishant is asking, so you got the I got the idea from this. Also, you should also remember this BIC inversion that this also occurs frequently in Olympiads. So I used this problem essentially to introduce BIC inversion to you. So another fourth inversion is the BIC inversion. And in this, you have seen these points map to these points have nice properties. Essentially, the main idea behind, or the motivation behind this, is that if you have a point M and you have points A and B, then MA times MB is fixed. And this is actually equal to, if you call this C and D, this is equal to MC square. So the whole idea behind doing the BIC inversion is this lemma. This is referred to as the shooting lemma. I would suggest not to use this name, or you can just say it's commonly known also. You can also say shooting lemma though, doesn't hurt. I am pretty sure you can use this on InMo also. Okay, so don't worry about that.
This is something similar to what we did, na? Like A is the point E and B is the point X we denoted.
Right. So this is then T, the same thing happens for T and D, same thing happens for A and A dash. So essentially you guys all points on the line, and then you can just simply angle chase. So working with lines is somewhat easier. Like now you have lots of collinear stuff, so you can do more manipulations. Sometimes working with circles is easier because you have the inscribed angle theorem and stuff. Okay. So let's just do a small question. Suppose you have 3 tangent circles. C1, C2, okay, omega 1, omega 2, omega 3. Omega 1, omega 2, omega 3. Prove that there exist 2 circles, small gamma and capital gamma, which are tangent to all the 3 circles.
So one must be internally tangent and one must be externally.
Right. Okay, so I'll just give the proof as such because we haven't really discussed what happens to tangent circles. So, okay, what I'll do is let like omega 1 touch omega 2 at point A. Let this be point B and let this be point C. So if I can, what I'll do, I'll invert with respect to A at random with any arbitrary radius, right? So I have A here and omega 1 passes through A, correct? That means it becomes a line not through A. And so same thing happens to omega 2. This just becomes omega 1 prime and this will become omega 2 prime. And since these circles, two circles are tangent, they would be parallel because they do not intersect at any other point. Do you see why this is true? Is there anyone who does not understand? Because see, if these 2 points actually intersected on some other point K, then they would also intersect at the pre-image of K or the image of K dash in the original figure. However, they do not intersect at any other point. This implies that omega 1 prime and omega 2 prime are actually tangent lines. Do you all understand this?
Yeah, parallel
Yeah.
lines. Got it.
Can anyone tell me what happens to omega 3?
Becomes circle tangent to both the parallel lines.
Right. Becomes circle tangent to both parallels. Good. So now what do you want to prove? You want to prove that there exist two circles tangent to these two lines and this circle. But that's pretty easy, right?
It's trivial because there'll be one
Yeah,
on
it's trivial.
each side of the
One
circle.
right. One circle will be here, one circle will be here. And you can also construct this circle, right? Because you can get these 2 points and then you can construct their inverses. Because you now get the three tangent points of the circle with the 3 circles. You can construct their inverses using the method we discussed in the beginning. So this is a really nice problem. This problem I believe is called Apollonius' problem. No, I
Can we
said.
also say the three circles will be like similar, not similar, congruent?
You can't call them congruent because the radii will change based on their position, right? Because say I have A and this is one circle and this is say another circle. Its center is here. Then B will map to some point here. This dude will map some point here. Whereas this person will map this person will go pretty much farther because it's much closer to the uh, center of inversion. So now this circle and this circle will have different radii because the diameters are different. Do you understand this?
No, but in the figure, like the perpendiculars make the diameter, no, and the distance between both the lines are equal, so the diameters has to be equal.
Yes.
No.
So and the inverted figure, all three circles have equal radii. But in the original figure, they will not have equal radii because their distances from A are different.
Okay.
So, okay. If I have two circles and this one slightly farther and smaller. If I look at the diameters, then this point will go somewhere here and this will be somewhere slightly closer. And in this circle, this point is closer, right? So this will go somewhere farther and this point will be much closer here. So now if you can see these two circles, okay, have different diameters and hence they will be having different radii. Or you can also think of it maybe if using the distance formula again. If this was A and B, then A dash B dash would be R square times AB upon if you call this under CA dash times, sorry, CA times CB. So the distances C and CB matter here. Because in this case, if these 2 points were say X and Y, and this is X and Z, then you get that X dash Z dash would be R square times XZ by AX times AZ. Whereas in this case, X dash Y dash would be R square times XY by AX times AY. See, the distances are not same because these two distances are not same.
Yeah, okay.
Okay. Does anybody have any other doubts? Questions? Comments? Okay, I'll stop the recording.